Welcome back, everybody. So you probably saw the quiz grades go in. I got those graded very quickly because they were pretty good. So I'll hand those back once everybody takes them. But they should be back in your hands probably by tomorrow. Here is the rundown for the rest of this week. I do not plan on wanting to assign homework over break or anything like that. So here's what I would love to do. I want to do the notes today and tomorrow, and then just leave Friday open as a work day. And then once you get back after spring break on that Monday, I'm going to give you time to work on that Monday as well. Because this is a pretty important section. I'll leave it open for questions at the beginning of class, and then I'll leave you time for you to work on that Monday as well. So don't feel like it's due on the Monday you get back. You will have that Monday to work as well. And that also gives me, I had 3 days worth of videos last year, but I feel like there was something weird going on. Like there was a late start or something in there last year for this section. I looking at the notes, I feel like I could get this done in 2 days. Because I packed away a little bit. All right. So today is when we start using the word integral. Okay. Today is when we start. I've kind of been using that word as we've gone along. We're talking about derivatives. We're talking about the sums and everything like that, and the area under the curve. Okay. But now we start using that term integral. Okay. We saw in section 5.1 that the limit of the form, and we had this limit. We know what this says, right? The limit as n goes to infinity, going from 1 to n. And this is basically, length. No, this would be length times height of a rectangle, right? Those are the length times heights of our rectangles, right? That's what we really talked about in section 5.1. Creating those rectangles, finding the areas of all of those rectangles, but multiplying width times, or the length, whatever you want to call it, times the y value, times the height. Difference in the x times the y value, right? And that summation notation is basically saying, well, I'm going to take x1 multiplied by delta x, x2, the y value multiplied by delta x, and so on and so forth until you get to the last strip, the last rectangle, f of xn multiplied by delta x. Okay, that's the area. We also saw that computation arises when we try to find distances. Come to get me. They found me out. It turns out that the same type of limit occurs in a wide variety of situations, even when f is not necessarily a positive function. We'll talk about when it goes positive or negative. They reference chapters 6 and 8, but we won't even get there. That's Calc 2. So it does come up again and again. So let's talk about what an integral says. Definition of the definite integral. It says, if f is a function defined on some interval, okay, we divide the interval a to b into n subintervals. So this is not saying like a particular amount. This is generalizing it to n, into n subintervals of equal width delta x. This is not new. That formula, not new. Same thing that we had, where delta x is equivalent to b minus a divided by n. And we're talking about over a period of time. And this is what, that period of time, that length, that definite length is what's going to separate definite integral to indefinite integral, which is the title of a section pretty soon. Definite integral to indefinite integral. Definite integral is when we have a to b. That's it. Just a to b. And we can say we're going to let x sub 0 be a. And we say, okay, then let x1 be a plus delta x. x2, a plus 2 delta x. x3, a plus 3 delta x. We'll talk about that again today. All the way till you get to b. And they're going to be the endpoints of those subintervals, and we let x1, they say there's an asterisk, be sample points in those subintervals that lies in those subintervals. it's interesting to point out that we're going to let those be some point in that interval. Please understand, like we were talking about left side and right side sum to get an underestimate or an overestimate, right? We're talking about left side sum, left rectangle approximation, right at rectangle approximation to get some sort of boundary, right? We know this is going to be an under, this is going to be an over, and we can say, well, the true area is somewhere in the middle. Well, what if I don't even let that necessarily, what if I don't force that to be an endpoint? What if I say, okay, in that interval, I'm going to choose a point somewhere in that interval to calculate the area for that given rectangle. And that's what they're saying here with this little asterisk. It's got to be sample point somewhere in those sum interval. We did left, we did right. What if we did mid, right? Which we'll have to do in this set of notes, doing midpoint approximation rather than left side approximation or right side approximation, midpoint approximation. So if that's all true, which is basically a summarization of everything we learned in section 5.1, then the definite integral of f from a to b is written like this. This is what we had learned in section 5.1. But mathematicians are lazy, We like to write things a little bit more compactly, write it a little bit more succinctly. They said, well, let's create this notation that allows us to write that limit out without having to write the limit out every time. And this is the integration notation, the integral notation. Okay? That is the integration notation. We can read this as the integral from a to b of the function f. That's how we read that. The integral from a to b of the function of the function f. And all that's saying is that's going to give you some function f. I don't know what it looks like. You've got boundary lines at a and b. This is defined as that region. That whole thing is equivalent to the area under the curve. Not the curve, but the area under the curve. Definite boundary lines, right? Definite boundary lines. Finite boundaries. We're going to find that some functions, just like we had some functions where you could find the derivative of and some functions you could not find the derivative of, we call those functions differentiable or not differentiable. Same thing is true for integration. We could have functions be integrable. I don't know where the like the accent is. Is it integrable or integrable or integral? No, I don't know. You can find the integral, right? Sometimes you can find the integral, sometimes you can't find the integral. It all kind of depends. Now we're not gonna dive too deep into integration. We're just gonna look at the basics of integration in this last chapter. Just know that if you go on to Calc 2, you kind of go a little bit deeper. That's where Calc 2 begins, just where Calc 1 leaves off. You start with a little bit more in-depth integration. Just like you can find single derivatives, you can find single derivatives and double derivatives. You can find single integrals and double integrals and even triple integrals. Interestingly enough, guess what? So if a single integral is area, what do you think a double integral is? Volume. So you can actually find the volume of something given a function by taking the double integral of that thing. And you know what it does? Basically, if you have 3 dimensions, if you've got this weird wacky function and the single integral is the area under the curve at that point from a to b, then the double integral is if you spun that function around the axis. The double integral would be the volume if you spun it around the axis. It's really kind of cool. Makes you want to take Calc 2, right? Let's just go right from Calc 1. Just me? Okay, cool. All right, but this is the integration. Now, where does that symbol come from? this integration symbol, right? It doesn't that kind of look just like a stretched out S? That's where it came from, just like a stretched out S. Like if a mathematician had really sloppy handwriting and just wrote the S in a really stretched out way, S for sum.
Pardon the interruption. Students that are going to Bridgestone, please go to door 9 now. If you are on the field trip to Bridgestone, please go to door 9 now. Yes.
So this is the integration notation. You put the lower boundary here. You put the upper boundary here. Right? You put your A on the bottom. You put your B on the top. Okay. You put the A on the bottom. You put the B on the top. So A goes down here. B goes up here. To the right of the integral symbol, you have to write the function. Now, we're going to just generalize it to be f of x, but that's where you would write whatever function you're finding the integral of. So if you wanted to find the integral of x squared, you'd be writing x squared right there. Next to f of x, you have to write the notation dx. Okay, that is always there. That is always there, fx dx. Where does that dx come from? Well, look at the summation notation. Isn't the differential on x another way to say dx? Right? The difference on x. It's just the calculus way to say it. Dx. And, you know, we're thinking about it in terms of differential here, but honestly, that kind of has like a derivative feel, right? And I've already talked about how antiderivatives are going to play a role, right? So now we can kind of see, well, if this whole thing is what I'm finding the integral of, I may need to take an antiderivative on a to b to find what the area is going to be. But again, that's going to come a little bit later. Okay. I'm talking about the symbol here. The symbol, this stretched out S-looking symbol, the integral symbol, was introduced by Leibniz and is called the integral sign. It is an elongated S and was chosen because it is the limit of sums. S for sum. In the notation, the f of x is called the integrand. Like this function is what you're finding the integral of, so it's called the integrand. A and B are called the limits of integration. A is the lower limit, B is the upper limit. It goes in the bottom, then the top. For now, the symbol dx really has no meaning by itself. It's just there as a placeholder to say, okay, that remember that you're finding the differential on x. It's kind of like just a reference back to your delta x, right? Just to remind you, okay, that's your delta x. You're taking your f, your y values multiplied by delta x. The dx simply indicates that the independent variable is x. Yeah, and that'll be another indication where what the x value truly is. The procedure of calculating an integral is called integration, obviously. That x could be written as any letter there. Okay. We could have fx dx, ft dt, fr dr. Just notice that these independent variables have to always be the same, whether you're choosing x or r or t or a. Don't choose a because a is the lower limit. But whatever variable you're choosing to find, that's the f of blank d blank. Those letters must always match. Okay. I kind of have referenced what's called the Riemann sum. We're going to be finding Riemann sums in this section too. Honestly, you found 2 Riemann sums on your quiz. Right? You found 2 Riemann sums on your quiz. You just didn't really call them Riemann sums. This is the Riemann sum. From 1 to n, and I'll tell you what n is, how many things you want to break it up into, of fxi times delta x. It's called the Riemann sum after German mathematician Bernhard Riemann. So definition 2 says that the definite integral of an integrable function can be approximated with any desired degree of accuracy by a Riemann sum. So you can approximate the integration by using a Riemann sum. So what we're going to be doing the first couple times we do integration, what we're going to do is we're going to use our properties of integration, and then we're going to estimate it using the Riemann sum and see how closely those two things match. Okay? The reason why Riemann sums are useful is because some functions are not integrable. Okay? Some functions you can't find the integral of. So if you can't find the integral, maybe you can approximate it using a Riemann sum. Okay? And we don't even know the process of integration yet. We're still kind of ambiguous on that. One thing, I just kind of want to jump to the bottom of this page a little bit. Know that areas, we've been looking at areas above the x-axis. You can have an area below the x-axis as well. You just calculate it as a negative area. Okay? I know we say areas cannot be negative, and it's just kind of moving into the negative direction there. Okay? So yeah, you can have a negative area. If it goes below the x-axis, you just calculate that area as negative area. The net area is the integration. Okay. I don't think we need to talk about this. All right, let's get to this. Let's get to our first example here. So all I'm asking you to do here is just change the notation. Okay? Change the notation. Just go from this limit notation, and we're going to write it as an integral. Okay? So first thing here is that I see my interval that I want to find the integration on, right? That I want to integrate on. So I'm going to say from 0 to pi. 0 is my lower boundary, pi is my upper boundary. I'm going to write it like that. Next comes my function. Well, I basically can just rip this straight out of here and just take off the i's. So it's going to be x cubed plus x sine x. Ooh. And then dx. And that's a heck of a lot easier than writing the sum all the way out. Right now, again, we don't know how to calculate that yet. That's what we'll learn in the coming sections, the end of this section and the rest of it. But for right now, this is all we know. Just how to write it as an integral. Okay. Take a look here. Do I want to tell you about this yet? I do. Okay. Now, I'll just jump it back. Can I do it on the next slide? Yeah, we'll do it here. So I'm going to evaluate the Riemann sum for f of x is equal to x to the third minus 6x, taking sample points to be the right endpoints, and a is 0, b is 3, and n is 6. Understand this. Like, look at this notation and understand it. A and B are asking you the exact same thing. But A is an approximation where B is an exact value. And I'm going to teach you how to find the exact value. I'm going to teach you how to find the exact value for the approximation. So let's take a look at it. Oh, where'd that example go? Where's example 2? Oh, there it is. Okay. So the first thing I want to talk about here is, I don't necessarily know what this function looks like, and I don't really care if I want to draw out what this looks like. I don't really know whether this is going to be an under approximation or an over approximation. All I want to do is calculate the Riemann sum. So what is the Riemann sum again? The Riemann sum is this here. sum going from 1 to n, fxi delta x. Let's write that in there. Sum, this is a. This is the sum from I is equal to 1 to n of f of xi, right? F of xi delta x. That's the general form of the Riemann sum. Let's evaluate that Riemann sum for x to the third minus 6x on a to b, 0 to 3, for n equals 6. Okay, so let's change this notation and say, well, I'm going to go from I is equal to 1. Now, what is n in this case? 6. On x to the third minus 6x those are i's down there, dx, delta x, sorry, not dx, delta x. What is delta x in this case, though? Well, we can evaluate delta x as b minus a over n. So in this case, I've got 3 minus 0 over 6. So 1/2. Now, let's evaluate what our xi's are going to be. Right? What our xi's going to be. Now, think about this. If I am choosing right side endpoints, let me kind of draw it out a little bit. You know what? I'll do it on the screen so everybody can see it at home too. You're streaming along at home. If I've got my function here, again, I don't know what this looks like. And I'm using right side endpoints from A to B. Am I going to be using the y value here? If it's a right side endpoint, am I using that y value? No. What's the first y value that I'm going to use? x1, right? That's the first y value that I'm going to use because that's my true right side endpoint. Am I going to use B? Yeah. Right? Because that's a right side endpoint. So you just got to think through it logically. So really, I'm using my first x value is going to be x1. My first x value is going to be x1. And that's going to be a plus delta x. Well, what is a in this case? 0. 0. 0 plus delta x. Delta x is 1/2. So 1/2. x2. That's going to be 0 plus 2 delta x. 2 times 1/2. Well, that's just 1. x3. That's going to be 0, not times. x3 is going to be 0 plus 3 delta x. So 1.5. x4. That's going to be 0 plus 4 delta x. That's going to be 2. x5. That's going to be 0 plus 5 delta x. That's going to be 2.5. x6. That's going to be 0 plus 6 delta x, which is going to be 3. Notice that I stopped there because I'm using 6 strips. I've landed at my endpoint. Am I going to be using 3? Yes, because again, it is right side endpoint. Okay. Let me erase my diagram here and put the sum over here. So this is telling me that I'm going to use 1/2 times all of these y values. And again, there's 2 different ways to write this. I like to factor out the 1/2 and then write the sum of the y values. You could also take the x times the y each one, but I don't know. It's writing a lot. So now I'm going to take f of 1/2 plus f of 1 plus f of 1.5. I'm going to run out of room. Here we go. Plus f of 2.5 plus f of 3. Everybody follow me there? Now, here comes the hard part of just plugging it into the equation, right? Just plugging it into the equation. I got to plug in 0.5. I did try to do square root of 9. Teach my algebra students about that. But I've got to take x to the third minus 6x, right? So it's 0.5 to the third minus 6 times 0.5. Okay, that's going to give me that. And I'm going to just keep adding. 1 to the third, which is 1, minus 6 times 1. Right? Plus, and then I've got 1.5 to the third, minus 6 times 1.5. Right? Plus, let's do 2. 2 to the third, minus 6 times 2. Plus, and this is going to give me 2.5 to the third, minus 6 times 2.5. Plus, and then we do 3. 3 to the third, minus 6 times 3. Negative 7.875. And I'm going to multiply all of that by 1/2, delta x sitting on the outside, times 0.5, and that's going to get me negative 3.9375. So let's say negative 3.94. Right. That's the Riemann sum from 0 to 3, where n is 6. Now, the more difficult the function, the more difficult the problem. The more strips I ask you to take, the more lengthy the problem becomes. It's a relatively simple process, right? Now, here's the deal. I can do this in a lot cleaner way. A lot cleaner way. I had said that integration, or finding the area, which we'll now call integration, ties right in with antiderivatives, right? Ties right into antiderivatives. So here's the fun part for today. I'm going to tell you that this from a to b of fx dx is equivalent to, we got fx a b. Now look at that notation. Those two statements are equivalent. The integral from a to b of f of x dx is really now what is this? What's capital F? The antiderivative a to b. Now what is this notation saying? This notation is saying, okay, here's my here's my right side endpoint, here's my left side endpoint, and all you're going to do is do top minus bottom. You're going to plug in the top, then you're going to subtract from the bottom. So what does that mean in terms of this? Well, my function was x to the third minus 6x, and we're finding it from 0 to 3. So in integration notation, I've got x to the third minus 6x dx, right? That's the integration. Okay, so that means that's equivalent to, well, what is the antiderivative? It's x to the fourth over 4 minus 6x squared over 2 from 0 to 3. Or in other words, x to the fourth minus 3x squared, x to the fourth over 4 minus 3x squared from 0 to 3. Now, how do we calculate that? Again, it's top minus bottom, right minus left. I'm finding like the area, or the difference in the areas, right? Okay, so this means I'm going to take 3 to the third divided by 4 minus 3 times 3 squared minus, and you got to put this in parentheses here, 0 plugged in. 0 to the 4th over 4 minus 3 times 0 squared. Plug it in. Well, what's this going to be? 0, right? So I'm going to take this minus 0, so 3 to the 3rd divided by 4. Oh, why did I do 4? Why did I do 3 to the 3rd? That's weird. Change the power now. Sorry. 3 to the 4th divided by 4 minus 3 times 3 squared that's not coming out good. Negative 6.75. One over 4 minus, minus 27. Yeah, I guess so. Here's why I question that. What was my estimation? Not a very good estimation, I guess, right? If I had done a Riemann sum with a higher n value, I probably would have gotten a little closer. But so that's how you find the area underneath the curve. So what's this negative area telling me? What's this negative area telling me about the function? It's below the x-axis, right? It's at least the net area is below the x-axis, right? It could be above, it could be below. I don't really know here, but I'm guessing that it's probably all below. Let's stop there and we'll pick up with example 3 tomorrow. Okay.